Hello, my name is Bojan Mitov, the president of Mitov Software, and in this session I will demonstrate creating video, audio, DSP, computer vision, and animations with the Mitov Software libraries for Delphi and C++ Builder. Mitov Software offers a large number of component libraries for Delphi and C++ Builder. When working with video, audio, and signal processing, the following libraries can be used. VideoLab is a video processing library, AudioLab audio processing library, SignalLab digital signal processing library. In addition, Basic Video is available, which contains a subset of the components from VideoLab, and Basic Audio, which contains a small subset of components from AudioLab. These two libraries can be used instead of VideoLab and AudioLab when only basic playback and recording functionality is needed. Now let's switch to Delphi and see how we can use the libraries. We will start with new VCL application. We will add AVI player to play the video and image display to display it. We will switch to the OpenWire view, connect the video player to the image display, select File to Play, compile and run the application. You can see the video playing. In the video player component, you can also see a preview of the selected file. Now let's add some video processing functionality. The simplest task is to convert the video to a grayscale. For this, we will add a grayscale component and another image display. And we will connect the components together. The video from the video player will be sent to image display 1, also to the grayscale, and the result from the grayscale will be sent to image display 2. You can also see preview of what the result of image will be in the grayscale. Let's compile and run the application. Here is our first video processing application. You can see that the video is being converted to grayscale. Before we continue, I will set the video player on loop. We will add some geometric transformations, swirl, and yet another image display to display the result of the swirl. We will swirl the grayscale video. You can see the swirled video here. We can also add rotation and rotate the swirled video, as example by 30 degrees. And we can preview the rotation inside the component, as well as the swirl effect. You can see the processed video here. Instead of geometrically transforming the grayscale video, we can switch to processing the original video. Here is the original swirled and rotated video. We can also combine the two videos, as example with combine component. If we add another image display, we can combine, as example, the grayscale video with the swirled and rotated video and display the result on the new display. Here is the resulting combined video. Naturally, we can change to combine the original video with the processed one instead of the grayscale. And here is the result. Let's do some video analysis. We'll add a scope component and a histogram component. We'll use the histogram component to analyze the video and we'll display the results on the scope. We will analyze the swirl video and we'll connect the histogram to the scope. If we click on the pin list block of the histogram and then move the mouse over this button on the scope and click here, new channels will be automatically added to the scope and the histogram will be connected. Since the last channel is the alpha channel and the alpha is the same for all pixels in this video, we can ignore it and reduce the number of channels. If we run the application, you can see the histogram of the swirled video. Let's add some audio functionality. First, we'll add a component to hear the audio. We'll use audio out component and we'll connect it to the audio output of the video player. You can hear the audio of the video being played.
Of a peaceful life on an all-new episode.
We'll delete the component so it will not distract us from the video tutorial. Next, we will try to display the audio on a scope. We'll add another scope component, connect the audio pin to the channel of the scope. The scope will immediately show the first channel of the audio. Since the audio is stereo, if we want to see both channels, we will need to split them. For this, we can use audio to real converter. We will connect the audio to the audio to real, and we'll connect the audio to real to the scope. Now we can see both the left and right channels of the audio on the scope. Next, we can add some audio analysis. For this, we'll add another scope and a spectrum component from AudioLab. We will connect the audio to the spectrum and the spectrum to the scope. Here is the spectrum of the audio. You can see the different frequencies represented in the audio buffers of the left and right channels. There are other ways to represent the same information. As example, if we use Instrument Lab, we can also use the spectrum component from it. We will add spectrum display and we will connect it to one of the channels of the spectrum. We will set a lower order for the spectrum. You can see the spectrum being displayed. We can also display it in a waterfall component. Again, by changing the order, we can customize the number of frequencies displayed in the waterfall. Now we have many more frequencies in our waterfall component. The components from the libraries have a number of pins for different types of data. Sometimes, however, we need to add additional pins to control some properties. As example, if we want to control the angle of rotation with some other component, we can add a sync pin to the rotate component, and we can add a signal lab component to control it. We will use a sine wave to control the rotation. We will add a signal generator, set amplitude of 180, so it will go between plus minus 180 degrees, frequency of 0.1, and will generate one sample each time with 10 samples per second. Now we can connect the two components, compile and run. You can see the video being rotated based on the angle from the sine wave. With the help of Instrument Lab, we can also show the progress of the video that is being played. For this, I will add few Instrument Lab components: a segment clock component, a gauge, and a thermometer, and connect the progress pin to the three components. Since the progress pin is a state pin, a special object called state dispatcher will be created to dispatch the data to the connected components. We will need to set the time source for the segment clock from current time to value to display the progress instead of current time. Compile and run the code. You can see the progress of the video being displayed in the clock, the gauge, and the thermometer. We can also use the gauge and the thermometer to display the level of the audio. We will use the ppm meter component, but you can as easily use the VU meter. They both will display audio level using different approaches. We will connect the component to the audio and the gauges to the component. You can see the audio level being displayed with ppm meter in the gauge and the thermometer. The Instrument Lab components allow you to add elements to them. If I double click on the component, I will open the components editor, where I can add displays, gauges, indicators, clocks, panels, hands, images, and labels. We can add external segment clock element and an external thermometer element. In the OpenWire view, we can connect them, the thermometer, to the other ppm meter channel, and the external segment clock element to the progress. For the external clock element, we can set the time source to be value. Compile and run. You can see the elements working, displaying the progress and the view level. Inside the analog gauge, we can add video display. I'll add image display, set its position to the center, and make it bigger. So it will take the whole gauge. Then I will connect the rotated and swerved video to it. You can see the video being rendered inside the gauge. And it is the same video being displayed on this display. Of course, we can also connect the original video and see it being played inside the gauge. We can also add gauges inside the video. For this, we can use the draw component from VideoLab. And we can add, as example, a clock component. We will connect the processed video with the two combined videos to the draw component and the output of the draw component to the image display form to see the result. Compile and run the application. You can see the clock being rendered inside the video. In the draw component, we can add video effects. As example, we can add fire effect. And you can see the fire being rendered inside the video. The fire effect can be applied to another layer. As example, it can be applied on the analog clock layer. We can add associated layer for the fire effect to be the analog clock layer. You can see that now the fire effect is applied on the clock. And we can send the resulting video after applying the layers to the image display element we added earlier to the gauge. And you can see the video being rendered inside the gauge. Instrument Lab includes LED matrix component. If we add matrix display, we can add elements into it. If we double click on the component, we can add clock and gauges. We can also add image display. And we can connect that image display to display the swerved video. You can see the video rendered in the matrix. We can also record and broadcast the video. We will add a video logger. We will use the LAV video logger, which is a relatively new component in the library. And we will specify a file where we will record. The LAV video logger automatically recognizes the extension of the file and will use the appropriate encoding. We can also broadcast the video. We will use the ASF broadcasting component for it. This component requires a profile to be selected. I have ready profile for our encoding. I will select the profile file and I will specify local port for the broadcasting. I will connect video from my combine to both the logger, and the broadcast component. And I will connect the audio from the player again to both components. We will see the firewall dialog appear, asking us for permission to broadcast through the 8080 port. We will allow that. Now, if we open Windows Media Player, we can open the URL and see the broadcast. And after a while, we'll start playing inside the video player.
Who are you? My name is Dan.
No battle.
We can also see that a result MP4 file has been created. And we can play it in Windows Media Player.
CMAC gets a second chance at a peaceful life on an all-new episode.
PlotLab contains another interesting component called multi-waterfall.
We can use it to display histogram data in a waterfall form. We can add 3 channels to it and connect them to the histogram component. Since the histogram will contain a lot of black and white frames, we can narrow the focus on the more meaningful colors to have more interesting waterfall representation. For this, we will increase the lower level to 10 and decrease the upper level to 245. And we can see our histogram being represented as a waterfall. We can zoom and study the data.
It is also easy to create video capture applications. We can add DS capture component and image display. Connect the components and we can see the video being captured. We can also capture from IP camera. For this, we can replace the DS capture component with IP camera component. Set the RTSP URL of the camera to the URL property of the component and connect the components. You can see the video from the IP camera. We will go quickly over some other Video Lab features. Here are some different ways to combine video. Here we have 2 files, one of them being rotated, and they are being combined with different ways, including copy, with alpha channel. We can also use free-frame plugins. With various effects. The library also includes a large number of remapping components, including fisheye, cylinder, swirl, and moving least square elastic warp. You can see the results of some of the remappings. The library also includes a vector scope component. You can see the vector scope being rendered. when we need to process data inside our code or generate video buffers, we can use the generic filter included in the library. The generic filter has onProcessData event where we can process our data. The data will be provided in the input, and we can send the output data through the out buffer. If we set the send output data parameter to false, the output data will not be sent to the next buffer. Here we will convert the input buffer to a bitmap that will be displayed on the screen inside the image. You can see the bitmap being displayed. In the generic filter, we can do direct processing between the two buffers and pass data from the in buffer to the out buffer after applying some transformation. Here are different examples of simple video processing. And here is the result of our video processing in the generic filters. We can also use the generic filter to do custom painting over the video frames. Here we will convert the input buffer to bitmap, we will do our custom painting, and then we will convert the bitmap into an output buffer. And we will use the TVL bitmap, which is a thread-safe bitmap class. When we start the filter, we will create instance, and when we stop the filter, we will release that instance of the bitmap. Here is our custom rendering. We can also use the generic filter as a source of video. In this case, we will connect it to a logger and we will send data through the generic filter from code. First, we will send a start command specifying the size of the frames in the video and some period between the frames. When we stop, we will send a stop command. While running, we will create a buffer from a bitmap and we will send that buffer to the generic filter. A recorded file has been created. And it has the bitmaps recorded in it.
VideoWrap can also be used to process individual bitmaps. In this case, we will process the bitmap inside this D image, performing different filters and geometric transformations. Inside the on-button click event, we will call process bitmap on the different filters. We will pass the input bitmap and the output bitmap, and the filtering will be performed. And here is the result of the processing.
With VideoLab, you can implement fully functional video players with syncing capabilities.
It's a weapon.
Where did you come from? Greatest enemy.
For an evil warlord's obsession to risk everything.
And you can switch between playing different video with video transition effects.
In FireMonkey, with the help of visual live bindings, You can also do rendering a video over three-dimensional objects, as example in Viewport 3D. In this example, we have added visual light binding to the light material source, and we have connected the video to it. We have also added visual light binding to the Y rotation angle of the cube, and we use the progress to control the rotation of the cube. We also have added visual light bindings for down-click events of the buttons, and we have light binding for the start, stop, pause, and resume methods of the DS video player. You can see that the video is being rendered over the cube. We can pause, resume, stop, and start the playback. You can see that you can create quite complex applications using VideoLab combined with OpenWire visual light bindings. VideoLab has many more component features and demos, but I will let you explore them on your own.
A quick tour of some of the Audio Lab features.
You can mix audio sources with Audio Mixer. Here we can mix WAV file with two signal generators, and we can play the audio and display it on a scope. You can control the level.
On the next Xena adventure.
What's in that tune that would drive me into
Enable
murder?
or disable channels.
My spirit has been trapped here in this tomb. I went out.
You can also plot the entire wave data and then later play and show the progress. We can load the file and then we can play. You can see the progress of the playback and we can
On the
sync
next Xena
Aries, the answer is no. Me into murder.
and change the
travels to
playback
the
position.
20th century where the forces of good and evil reunite.
Till they get a load of me.
Think
Pause,
again, Aries.
Battle on,
Resume.
Xena.
stop, and play again. AudioLab also includes components for VST plugin support, including VST3. With the plugins,
On the next
you
Xena
can
adventure.
perform
What's in that tune
variety
that would drive
of
me
effects
into murder?
over the audio.
Travels to the 20th century where the forces of good and evil reunite.
My spirit has been trapped here in this tomb. I went out.
Aries, the answer.
The library also includes goniometer component. You can see the goniometer processing the audio
On the
and
next
displaying it on
Xena
the scope.
adventure.
What's in that tune that would drive me into murder?
Xena travels to the 20th century where the forces
AudioLab also contains generic filters, and we can use them the same way as in VideoLab. As example, to process input-output buffers, or to generate and send data through the filter by sending start, stop commands, and send data commands. And you can see the generated and processed data. Now we will make our first digital signal processing project. We will start with VCL form application, add a random generator and a scope. We will connect the random generator to the scope, compile, and run the application. You can see the random data being displayed on the scope. Let's analyze the data. We will use fast Fourier transformation component to display the frequencies in the random noise. For this, we will add Fourier component and another scope. We will connect the signal to the Fourier and the spectrum from the Fourier to the second scope. You can see the frequencies in the random signal. We can replace the second scope with Waterfall and see the frequencies displayed over time. Next, we will add filtering. We will add a low-pass filter. We will connect the random noise to the low-pass filter, add one more channel to the scope, and connect the low-pass filter to it. You can see here the filter signal. We can connect the filter signal to the FFT and see the frequencies of the filtered signal. The components have built-in visualizers which allow us to see the random noise generated by the generator and the characteristics of the filter at design time. We can use a track bar and visual line binding to control the frequency of the filter. I will add a track bar we will add a source pin for the position property of the track bar. And for our low-pass filter, for its frequency, we will add a sync pin. We will set the max for the track bar to 50,000 and the min to 500. This will be our frequency range for the filter. We will connect the position of the track bar to the frequency of the low-pass filter. Now we can use the track bar to change the frequency of the filter. Next, we will create Lissajous figures application. For this, we will add two signal generators and a scope component. We will change the frequency of one of the generators. We will connect one of them to X of channel 0 and the other one to Y of channel 0. You can see the Lissajous figures. Similar to the previous project, with visual line bindings, we can control the generators with track bars. We will add sync pins for the frequency on both of the generators, add two track bars, set the maximum to 1000 and the minimum to 100. Add source pin for the position. And connect the two track bars. Now you can experiment with different frequencies and have variety of Lissajous figures. Lissajous figures are always a fun way to experiment with DSP.
When implementing computer vision applications, Vision Lab can be used.
Vision Lab contains a large number of computer vision components. One of the simplest is the motion detection component. It has on motion detected event, you can set up a sensitivity matrix.
If you run the application and start the video, you will see the motion matrix and the motions detected based on the sensitivity levels. There is canny edge detection component, hawk lines and hawk segments, hawk circles that can find circles in the image, find contours component that can find contours and their bounding rectangles. Here are the inner and outer contours and their count. Finding and tracking target components using optical flow. Hard detect objects component that can be used to detect faces. And eyes inside the faces. Extract robust features component that can be used for 3D reconstruction or frame-to-frame object tracking. Hawk component that can be used to detect objects such as people in crowd. Adaptive background subtraction component that can subtract the background and show the foreground objects. Chamfer matching contour component that can find objects in images based on contour, as with those cows in this image. Here is also a quite complex project done with 0 lines of code by simply dropping the components and connecting them together. Here we process 2 video files and perform variety of computer vision tasks on them, including motion detection, extracting robust features, finding hawk circles and line segments, finding and tracking targets, finding contours, detecting faces and facial features.
Whenever there is a need to animate properties of components, you can use Animation Lab. It is a universal timeline-based animation library. Animation Lab contains timeline component and physics effects components such as this mass effect. In your application, you can have many timeline components, and each of them can have one or more channels. The channels can be of different types. As example, color, Boolean channel, floating point channel, and they can have different types of interpolations. In this project, we will use Animation Lab to animate this cube, this rectangle, the index of this list box, and some labels. To animate the objects, we have added visual line binding pins to some of the properties. As example, the depth, height, and width of the cube will be animated by this timeline, and I have added pins for them. The timeline has one channel, and it will be started when the cube is clicked. Timeline 2 will change the color of the light material source, will make label 1 visible, invisible, and will enable or disable the mask component. Timeline 1 will provide width for the rectangle and will control the rotation angle of the round cube. Timeline 4 will control the item index of the list box. You can see the different objects being animated, including their color, size, rotation. And if I click on the cube, it will perform its animation. The mass effect also will be enabled or disabled based on the timeline. Here we have even more interesting project. Again, we have 4 timelines. However, they have many more channels with variety of interpolations, spline, and linear. Value change. There is also channel with events fired at specific times. String channel, Boolean channel, color channel, and 2 real channels. And here is another small timeline with 4 channels, real channel with cubic spline, alpha color channel with 2 linear interpolations, 1 Boolean channel, and a string channel with different strings shown at different time. Here is the connection diagram for the project. You can see the character being animated, and if I click on it, it will perform a short animation, including showing text. This bow here also is animated, and we can trigger animation by clicking on it. The animation is also triggered at specific times by another timeline. And the mass effect is enabled or disabled over time. As example, this is without mass effect. The libraries we demonstrated can be combined with the rest of the Mitov Software libraries, including Plot Lab, Instrument Lab, Intelligence Lab, Logic Lab, and Communication Lab. This concludes our session. My name again is Bojan Mitov, the president of Mitov Software. Mitov Software has a number of products for video processing, audio processing, digital signal processing, computer vision, data visualization, visual instrumentation, artificial intelligence, Boolean logic, universal animations, serial and TCP communication, visual line binding library, and a free advanced runtime library. We also develop the OpenWire Studio, a graphical development environment for Windows, and Visuino, a graphical development environment for Arduino. Mitov Software also supports the OpenWire open source library and the IGDI Plus open source library. Thank you for listening, and now it's time for questions and answers.